two types of magnetism which are induced and permanent. Induced magnets only becomes a magnet when it is placed in a magnetic field. The induced magnetism is quickly lost when the magnet is removed from the magnetic field. Features: only attracted by other magnets, they are not repelled. Lose most or all of their magnetism when they are removed from the magnetic field.
Let's move on to the permanent magnet. It is often made from a magnetic material such as steel. A permanent magnet always causes a force on other magnets, or on magnetic materials. Features: it produces its own magnetic field. The magnetic field cannot be turned on and off, it is there at all time. Moving on, magnetic materials. It may be classified as hard or soft. Hard material retains magnetism well, but difficult to magnetize in the first place. Example of it is hard steel. The uses are compass needles and permanent magnets. Next, soft material. It is easy to magnetize, but readily loses its magnetism. Example of it is soft iron. The use of it is transformers. Subsequently, magnetic fields. A magnet affects any piece of magnetic materials that is nearby. We say that there is a magnetic field around the magnet. We represent the magnetic field of a single bar magnet, using magnetic field lines. Of course, the field fills all the space around the magnet, but we can only draw a selection of lines to represent it. The patterns tell us two things about the field. One is the direction. If you were to place a tiny compass at a point in the field, it would align itself along the field line at that point. Second is the strength. Lines close together indicate a strong field. Electromagnets. Only one way of making a magnet is using magnetic materials. An alternative method is to use an electromagnet. A typical electromagnet is made from a coil of copper wire. A coil like this is sometimes called a solenoid. When a current flows through the wire, there is a magnetic field around the coil. The copper wire is used often because of its low resistance. The coil does not have to be made from a magnetic material. The point is that it is the electric current that produces the magnetic field. There are three ways to increase the strength of an electromagnet. First is to increase the current flowing through it, because the greater the current, the greater the strength of the field. Second is to increase the number of turns of wire on the coil. This does not mean making the coil longer, but packing more turns into the same space to concentrate the field. The third is to add a soft iron core so that it becomes strongly magnetized by the field. We saw that an electromagnet can be made by passing a current through a coil of wire. The flow of current results in a magnetic field around the solenoid. If you uncoil a solenoid, you will have a straight wire. With a current flowing through it, it will have a magnetic field around it. Every electric current is surrounded by the magnetic field that it creates. An electromagnet is simply a clever way of making use of this, because winding the wire into a coil is a way of concentrating the magnetic field. To find the direction of the field lines, you can use the right-hand grip rule. The way to do it is to hold out your right hand with your fingers tucked in and your thumb pointing upwards. The thumb is equal to the direction of current. The fingers are equal to the magnetic field direction. The motor. How an electric motor works. A current flows in through the right-hand brush, around the coil, and out through the other brush. When the current is flowing, the coil becomes an electromagnet. The north pole of the coil is attracted to the south pole of the permanent magnet on the left, so the coil starts to turn to the left. There is where the commutator comes in. The coil is attracted round by the two permanent magnets. Its momentum carries it past the vertical position. Now, the brush connections to the two halves of the commutator are reversed. The current flows the opposite way around the coil. We again have a north pole on the uppermost side of the coil, so it turns another 180 degrees anti-clockwise. Without the commutator, the coil would simply turn until it was vertical. The commutator reverses the current through the coil every half turn, so that the coil keeps on turning. Lastly, Fleming's left-hand rule. The way of doing this is: hold your thumb, index finger and second finger at right angles to each other. The index finger is lined up with magnetic field lines pointing from north to south. The second finger is lined up with the current pointing from positive to negative. The thumb shows the direction of the motor effect force on the conductor carrying the current. We use Fleming's left-hand rule to predict the direction of the force on a current carrying conductor in the magnetic field.